I am going to explain in this video some basic concepts to express the strength of solutions. There are different ways to express the strength of solution, and the simplest one is called percentage, and so its symbol is this percentage. First we'll see the definition. So it is defined as the number of grams. So number of grams of a solute, per 100 gram of solution, So if we say, for example, 40% salt solution, so it means 40 gram NaCl and 60 gram water. This is the simple meaning of the term percentage. This percentage, it can be in terms of mass percentage, it can be in terms of the volume percentage, but the point is we take the mass, so it can be expressed in different ways as follows. So it can be in terms of mass, it can be in terms of the volume. If we have two components, if A and B are the components means let this be solid, this be solvent, or anything can be. So mass percentage of A will be equal to amount of A upon amount of A plus B into 100. So this mass percentage, this is first mass percentage. So simply mass percentage we take in terms of the gram, amount of A in gram, amount of A and B in terms of gram. Then there can be the volume percentage. So if there is the A, so here we take the volume. So volume of A. So volume will be measured in terms of ml, and then volume of A plus B in ml multiplied by 100. There is third option also, that is volume upon mass percentage. Third is volume upon mass percentage. So it can be either mass upon volume or it can be volume upon mass. Actually, these different ways are used to express the strength of liquid medicines rather, cup syrups and different solutions. So they are expressed in terms of mass. So third is mass volume percentage. So similarly, if we have component, let it be component A. So here we take the mass of A again in gram upon volume of A plus B again in what? Again in ml and multiplied by 100. So this is all about the percentage of three different types in different conditions. Now second is ppm. ppm means parts per million. So it is simply number of parts of one component present in 1 million part of other component. So it is defined as number of parts of a component per million part of the mixture. It can be mixture, it can be solution. We can take anything. So it is our ppm, and we accordingly it is changed. So ppm can be written as ppm can be written in the simple words, and so mass of A, mass of the component, just A or B, it is our own interpretation. So here mass of A or B, we can have the mass percentage of A or B both. Here I have taken A, it can be B also. So here the total mass into 10 raised to power 6. So this is the ppm, parts per million. Like you see on the packets of the common salt, it is written, iodized salt. So iodized salt has certain fixed norms with respect to WHO, and so it is written around 13 ppm. So a permissible value of the potassium iodide or potassium iodate in common salt is 13 ppm around. So it is there about the ppm. Similarly, the pollutants are measured in terms of ppm also. So ppm is very microscopic quantities, very minute quantities, very minor quantities are expressed. It is very minute quantity measurement in it. Now third one is molarity. Molarity, and its symbol is capital M, and it is defined as the number of moles of solute per liter of solution. Number of moles of solute present in per liter of solution. So we define like this, and so this is very important to note that molarity M. So number of moles, amount of substance, let it be MB. Number of moles, or say if we say here NB. And so similarly we can change like this. So number of moles is equal to the quantity. Number of moles is equal to the quantity given. Now one point about the molarity is that molarity, as it involves the volume, so molarity is affected by changing temperature. So molarity is affected by temperature or by change in temperature. When there is a temperature variation, because we measure volume of any liquid by vessel. So when the temperature is affecting the volume, it means molarity is not good way to express the strength of solution. So it is not regarded as a best way to express the strength of solution. Because when the temperature is high, what happens? There is the expansion in volume, and when temperature is low, there is the contraction in volume. So keep in mind that molarity is not regarded as better way or best way to express the strength of solution, as it depends on the temperature. Now fourth is molality, and its symbol is small m. Molarity symbol is capital M, molality has symbol small m, and so it is defined as the number of moles of a solute present in 1000 gram of solvent. This is molarity has number of moles in 1 liter of solution or per liter of solution, but it is number of moles of solute present in 1 kg or 1000 gram of solvent. This is the very important point. First we see the definition. So it is defined as the number of moles of solute per kg of solvent, per kg of solvent. Now this M, again number of moles is there, so similarly we have here WB means the amount of solute, here MB, it will remain the same, similar to the molarity, here into 1000, but here there will be W. This W this is the weight of solution, weight of solvent in gram. So this quantity, that is, this is the number of moles, and so this quantity is same with that of the molarity, but here it is this difference. Now this is a best way. You have to keep in mind that molality is the best way. It is best way to express the strength as it is independent of temperature. What is independent of temperature? It is independent of temperature. Why? Because the mass is unaffected by temperature. So it is best way with respect to what? Molarity. So keep in mind that between molarity and molality is the best way as it involves the mass, and mass is not affected by temperature. Now next important method or way to express the strength is mole fraction, and mole fraction is represented, or it has the symbol X, and here actually it is a ratio. It is defined as the ratio of number of moles of a component, to the number of moles of all the components, So if we have suppose two components A and B, so accordingly it will be changed. Like this. See. Now I am going to explain next very important part, and it is normality. Normality, it has symbol capital N. Normality capital N, and so it is defined as number of gram equivalent, of a solute, per liter of solution, number of gram equivalents. So the question is, what is the meaning of gram equivalent? So gram equivalent is equal to when equivalent weight is expressed in gram. When equivalent weight is expressed in gram, let's see how. So I'm going to tell how to find out the equivalent weight of any acid or base. Equivalent weight of any acid or base. So equivalent weight of an acid or base. How to find out the equivalent weight? So it's very simple. Equivalent weight. So we take the molecular weight or molar mass upon acidity or basicity. Acidity or basicity. Now, you know, acidity is for the bases. It is for the bases, and this basicity is for the acids. Acidity is for the bases and basicity is for the acids. We'll see what is acidity and what is basicity. So acidity means, or it is defined as, number of replaceable hydroxyl ions per molecule on dissolving or on dissolution in water. Number of replaceable hydroxyl ions per molecule of as it is. So on dissolution of a base. So if you take NaOH, so NaOH on dissolving, it will form 1 mole of sodium ion and 1 mole of OH ion. So here this NaOH is called as mono. It will be called as monoacidic base. Similarly, monoacidic base. If you take this calcium hydroxide, so calcium hydroxide will give calcium ion plus 2 hydroxide ions. So this calcium hydroxide will be called as, it will be called as diacidic base. It will be called as diacidic base. So this is the meaning of acidity. Now see next about the basicity. So basicity, as you know, it is opposite of the acidity. So basicity is number of hydrogen ions lost from one molecule of an acid. One molecule of an acid. Like here we have HCl. So HCl on dissolution forms 1 mole of H ion and 1 mole of Cl. So this hydrochloric acid is monobasic acid. Similarly, if you take H2SO4, sulphuric acid, so on dissolution that will give rise to 2 moles of H plus ions and here 1 mole of sulphate ion. So this sulphuric acid is said to be dibasic acid. So this is about the concept of acidity and basicity. Now we'll come to find out the equivalent weight of an acid or base. Now see how to find out the equivalent weight. Equivalent weight of NaOH. So this molecular weight of sodium hydroxide will be 40. So here we write down 40. Sodium 23, oxygen 16 and hydrogen 1. So it comes out to 14. And 1 OH ion will be replaced from 1 mole. So here it will be 1. So it comes out to be 40. So here 40 gram per equivalent. So here 40 will be the equivalent weight as well as the molecular weight. So in case of monoacidic base or monobasic acids, equivalent weight and molecular weight both will be same. Again I am repeating, in case of monobasic acid and monoacidic base, equivalent weight and molecular weight will be same, because here it will be the 1. So on dividing by 1 there will be no change. So this. Now in case of sulfuric acid, let the equivalent weight of sulfuric acid. So here hydrogen 2, sulfur 32 and this oxygen 64. So it comes out to be 98. And so here from this two hydrogen ions are replaceable. So here we divide by 2. So it comes out to be 49 gram per equivalent. So this sulfuric acid is dibasic acid. So in dibasic acid or diacidic base, the equivalent will be reduced to half. Equivalent weight will be reduced to half. So this is the concept of equivalent weight of acids and bases.